Alright, let's continue by improving the project architecture. The first thing I will add to this project will be hexagonal or clean architecture. This architecture, also called as ports and adapters. Basically, each microservice in this project will follow the clean architecture principles. In the next section, I have a separate lecture to go into details of this architecture. But basically, with this architecture, you will isolate your domain logic from infrastructure and outside dependencies. This will be achieved by separating the service into different deployable units. As you see, here I have different boxes for each of the components, and it implies that I will have different modules for each of them. So each of the layers, data access, messaging, REST API, and business logic, should be deployable separately. And this requires to have different deployable units as components, as you will see in the implementation section. The next step is to define input and output ports of your domain logic. So please note that all input and output ports that are interfaces are defined in the domain module. So here I will draw input ports and output ports for order service. These ports are nothing but interfaces that need to be implemented by adapters. So I will have some adapters in this architecture. The first adapter type is called as primary adapter, which is the HTTP client in this picture, and it will call the domain logic. Domain logic will implement the input ports, and these input ports will be used by the REST API. So if you think the data flow, I will call the order service REST API from Postman, and it will first hit to REST API component, which will have a controller class. Then it will use the input port that is defined in the domain logic and call the methods exposed by these input ports. To use the input port, REST API module will have a dependency to the domain module. Then it comes to the secondary adapters. These adapters will implement the output ports that are again defined in the domain layer. The data access and messaging components will have these secondary adapters. Now, if we continue data flow, after getting requests from clients and calling the domain layer methods, we will process the business logic, and after that, we'll use the output ports to call data access and messaging layers from domain layer. As I mentioned in the next lecture, you will see more detailed explanation of this hexagonal architecture. For now, I will add the same input and output ports to the payment and restaurant services. And also I will mark the primary and secondary adapters in those services. The second improvement to this project will be applying domain-driven design principles. So in the domain logic, I will apply strategic and tactical domain-driven design patterns and use aggregates, entities, value objects, domain services, application services, and domain events. Again, there is a lecture to discuss domain-driven design in detail, but to summarize, an aggregate is a group of business objects which always need to be consistent. These business objects are called entities. The core business logic will be handled in an aggregate through entity objects. Value objects are used to define simple immutable objects with domain-driven names. They don't have identifier and only contains value. An example is having a money object instead of keeping a big decimal Java type directly. Domain services are used to handle business logic that spans multiple aggregate routes, and the logics that cannot fit into any entity by nature. An application service is the point of contact to the outside of domain. So any other layer that wants to communicate with domain layer needs to use application service. Finally, domain events are used to send notifications to other services that runs in different bounded contexts. For example, in this picture, the domain logic in the order service will create an order created domain event and send it through payment service using Kafka topics. Here I will also write down the patterns that you will be implementing. Saga pattern, as mentioned, will have process and rollback operations. And rollback methods are used to handle compensating transactions. We need to combine Saga with Outbox pattern to obtain a consistent solution. And I will be using pulling Outbox table with a scheduler and keep the state of Saga, Outbox, and order in the Outbox table for each microservice. With the Outbox pattern, I will add a local Outbox table to the same database that a microservice runs. Then instead of publishing an event directly, I will first save the event into this Outbox table. To save into this Outbox table, I will use the same ACID transaction that the order service uses for the local database operations. So I will be sure that the event is created automatically within the local database using ACID transaction. The next step will be reading the events from the Outbox table and sending them to the message bus. To do that, I will use pulling Outbox table using a scheduler. The same architecture applies for payment service and restaurant service. So I will have schedulers in each service that reads the events from the Outbox table. Also, I will make sure that the scheduler will mark the events as sent if and only if it can successfully send the events to Kafka. We will see the details in the implementation section. The Outbox pattern will help to cover failure scenarios, such as ensuring idempotency using Outbox table in each service, preventing concurrency issues with optimistic locks and database constraints, and updating Saga and order status for each operation. I will make this text smaller to open some space. So, after completing Saga and Outbox patterns, I will revisit customer service as I mentioned and update it to use CQRS pattern. As mentioned, initially, I will use a materialized view with a trigger. But later, I will change it with event sourcing and create the customer data in a new table in the order service database. Finally, I will Dockerize the services and run them on a local Kubernetes cluster, and then deploy them on Google Kubernetes Engine to manage, scale, and deploy them easily using Google Console and G-Cloud command line interface. Alright, this is the big picture of the project, which is a food ordering system, as I mentioned. More details will come in the coming lectures, so I will see you in the next lecture.